Hello everybody, my name is Adhisakti Sahasrara Nugroho, and today I'll be presenting my Math for Economics 2 midterms. Okay, so for problem 1, we are given the following question. In the model of discriminating monopoly with an output quota, show that if the marginal cost of production is constant, there is no effect of the imposition of the quota in country 2 on the price and output in country 1. Explain this result. So from here we can, here we have to see what the question actually asks us. So the question is asking us to, when there is a change in the quota or imposition of the quota in country 2, is there any change on the price and output in country 1? We have to show that there is no change, no effect. When the marginal cost, wait, let me get my pen. When show that there is no effect when the marginal cost of production is constant. No effect. So in order to do that, we first have to assume that we're using the standard maximization of profit function equation for a discriminating monopoly. This is when QI is the quota imposed on each country, QI meaning Q1 and Q2, and PI are the prices, and PI is P1 and P2, and C is the constant marginal cost. So here we see the formula, the function that we obtain is the profit function, where pi is the profit. Pi of Q1 and Q2 equals to TR, which is total revenue, minus total cost, which makes sense because total profit is total revenue minus total cost. And this we can expand into these two values right here, P1 Q1 plus P2 Q2 for TR, and then C Q1 plus Q2 for total cost. And then from here, to see if there are any changes that happen when quotas are imposed, we first have to find the partial derivatives from the profit function earlier. So here we see that we need to derive the the profit function with respect to Q1. We get this right here, which is basically we have to derive in respect of Q1, with the top has to be P1, Q1, P2, and Q2. Basically everything that is inside of the this earlier function right here. So after we have derived everything and we have obtained the first partial derivative, we get this value right here, which I labeled as 1. And then we do the same thing for Q2 below here. Calculate everything here, and then we get the result for the partial derivative with respect to Q2. Okay, now that we have these two partial derivatives, how can we show the affected changes when quotas are imposed? So this is 1 and this is 2, just to label them to make it easier for me when I'm explaining. From here we can conclude that when there is an imposition of quota in country 2, which is this one right here, number 2, Q2 affects the profit function because it is present, because Q2 is present in the function number 2 right here. This means that both prices and output in country 2 will be affected if there is an imposition of quota on country 2. To further better explain that, the imposition of quota in country 2, which is Q2, is present in this formula right here. This means that since this formula is actually the formula that states the change of quota in the change of quota in country 2 in the profit function, we can say that when there is a change in Q2, meaning there's a change in the output quota in country 2, there will be a change in the price and output in country 2. That goes without saying. And then now, however, Q2 will not affect the profit function of country 1, as there is no Q2 value present in the function over here, function 1. This means that both prices and output in country 1 remain unchanged. as the imposition of quotas in country 2 occurs. So here we have shown that when there is a constant C, constant marginal cost of production, there is no change in the price and output in country 1 when there is a change in quota in country 2. But what does this actually mean, though? So we can further interpret this by saying, since there is no Q1 also in the function for country 2, we can assume that the imposition of quotas on country 1 does not affect the prices and output also in country 2. Therefore, we can say that these prices and outputs are actually mutually exclusive from each other, and mutually exclusive from each other when marginal cost of production is constant. To further interpret, because it's still a little bit difficult to imagine, we can just say that we can interpret this as a monopoly having independent production needs in each country they sell to. For example, a monopoly sells petrol, does activities in 2 countries, but only sells petrol that they produce in said country to the market of said country. So, for example, the monopoly here has a refinery in country 1 and a refinery in country 2, but only sells its products to said country's market, making it they do not have any relation with each other. That's my interpretation of question 1. And now for question 2, problem 2. We're given the following question. The consumer has the utility function u equals x1 minus c1 alpha and x2 times x2 minus c2 1 minus alpha, where a and b are real values. Where C1 and C2 are interpreted as the minimum amounts required for a substance, derive her demand functions, discuss their properties, and compare them with the demand functions derived in the cup noodles example. Okay, so from the question, we're given an objective function u, which is a utility function, and we can assume that if there is a utility function, objective function, sorry, we can assume that there is a constraint. And here I label the constraint as y, which is the price of utilities. And here we can see, this is the one given by the question, and then down here, this is what I labeled f as the objective function, and g as the constraint. With the f and g functions, we can create the Lagrange function, which is this long function right here, with lambda. Lambda is actually the indicator of change of the constraint, right here, right here. And from there, we can combine these, from here, there we can combine, this is basically the f, this is the f, and this is the g, basically. This is the f, this is the g, and combined with lambda, we can create the Lagrange function here. Now we can derive the function into its first partial derivatives, derive the Lagrange function with respect to x1, x2, and also lambda. We get these 3 partial derivatives. With the first and second partial derivatives that we found, we can find the values of lambda. So here I have created, basically I've listed out the first partial derivative here, but I've rearranged it to show that lambda is equal to this value right here. And I've basically done the same thing for the second partial derivative too, right here. So now we can set lambda equals lambda to find either x1 or x2. In my method, I chose to find x1. So, lambda equals lambda, this equals this, and then just basically I rearranged it and did like the, like the simplification, and I found x1 equals to this long value right here, which I won't say because it's too long. So now we know the demand of x1 using the Lagrange method. So now to find the demand of x2, we have to input x1 into the constraint. Long story short, I put it. This is the constraint right here, and then I inputted this one, which is the value that we got in the previous question, and I got the value, the demand of x2 as this. Okay, now that we solved what is x1 and x2, the demand of x1 and x2, what can we actually conclude? Okay, we can conclude a few properties about x1 and x2. C1 is the minimum consumption for the good of X1, yes, and it is the unaffected constant between the demand of X1 and X2. So basically, we see both we see both C1 in both of the demand functions. And also, we can separate the demand functions into two main parts, the variable part and the constant part. So basically, this is the variable part because it has the prices of 2 and 1 right here. And also over here, this is the variable part right here, prices of 2 and also just 2. And also there is the constant part, which is, I previously pointed out, which is C1. And then we also see that the demand of X2 is not affected by the price of C1. Oh, sorry, the price of P1, which is the price of X1. Because over here in the demand of X2, we do not see any P1. Okay, the question also asks us to compare this demand function with the Cobb-Douglas method. In order to find the Cobb-Douglas method of the demand function from the Cobb-Douglas method, we need to state the consumer utility and also the consumer budget constraint, which I've listed out right here. Then to find the marginal utility of good X1, we have to find which are the first partial derivatives of X with respect to X1 and X2. So this is the marginal utility of X1 and marginal utility of X2. Basically the same thing as just the first partial derivatives of X1 and X2. Oh, sorry, not X1 and X2, of U with respect to X1 and X2. We now can use this rule in order to find the demand functions. And a curious thing that I found was when I was doing this right here, it actually ended up with the same result as when I was doing lambda equals lambda in the Lagrange method. So since this value and let me find it, this value and this value right here is actually, this value right here is actually the same, we can assume that the demand functions using the Lagrange method and the Cobb-Douglas method is identical. Now we are still left with these very ambiguous demand functions right here. Right? So in order to interpret it better, I can use this example where function U is actually the usage of goods in a village, X1 is the output of corn, while C1 is the minimum amount of corn villagers need to sustain themselves, and X2 is the supply of rice, while C2 is similarly the amount of rice needed by the villagers to sustain themselves. Now, with this example, we can see a little bit better that C1 and C2 is the minimum demand required, minimum demand of goods of rice, which is X1, goods of corn, which is X1, and goods of rice, which is X2. This is the minimum demand. From the interpretation, we can also better understand why X2 is not affected with the prices of X1, P1. This is because, in our example, rice is a staple food, so it is not changed by the changes of price of corn. However, if rice gets cheaper, corn demand might drop as people want to buy more rice. So here we can see X1, which is corn, is affected by the price of rice, while X2, which is rice, is not affected by the price of corn, which is P1. There is no P1 in here. This is just a way for us to visualize how the function, the function in the beginning right here, is actually used in real life. That's my interpretation. Okay, so now for problem 3. We're given the following question: solve the cost minimization problem, min WL. I'm not going to read everything because that might be too long. Where R equals raw material, L is labor, and K is capital. ABC is bigger than 0, while A plus C is smaller than 1. We need to interpret the production function in this problem. So from here we already see, from here we can obtain, before I explain the objective function and constraint, we can see from this that A, B, C are real values and A plus C are point numbers. So they're either like 0.5, 0.4, something like that. So this can be interpreted as A, B, and C are constants that have real values and acts as a standard for the constraint. So basically, if in real life we want to find like a certain constraint, then A, B, and C are actually used as a way to sort of standardize it. So a revenue over here maybe 1,000, and over here K is maybe 2,000. You know, they're all going to be liable. They're all going to be liable to B, C, and A in order to create a standard constraint. Anyway, now back to the objective function and the constraint. We can find the objective function from the utility right here, and also the constraint right here. We can input this again into the Lagrange function using the Kuhn-Tucker conditions this time to find these four partial derivatives. Don't forget to make these three smaller than 0 and this one larger than 0, while all of these have to be bigger than 0. Now we can remove the lambda by doing the following steps. I set here 1 equals to 2, set partial derivative 1 equals to 2. And basically it's a very long, complicated method, but I simplified it into only 2 steps here. And basically we can find here W equals R over B, our first value. And then set 1 equals to 3, do the same thing, do the steps, and then we find here W over V equals to CR over A L times L plus BK, right here. And then over here, set 2 equals to 3, same thing, and we find the final value R over V equals to C BR over A L BK. Now we can find the value of L, K, and R to find the cost minimization. So basically what I did here, I found a lot of similarities between these two equations. So to make it easier, I just cross-multiplied them and compared them. And we can see here that they have very, very similar structures. And we assume that that A and A, L and L, BK, everything has the same value, right? So we can therefore combine, achieve this new value, a new equation, A times L plus BK times R minus W equals to VCR times B minus 1 as our sort of final equation. From here we can arrange it into this form, which takes the form where we can see L, K, and R on the left side and then the rest on the right side here. So what can we actually, before we interpret this, we can actually go further and insert this value into the constraint. However, the results are very ambiguous and don't make much sense because it's just more letters, right? So just to show you, this is the value I obtained after inserting L, K, and R into the constraint, is this value right here, which actually gives us the result for revenue is bigger than all of this, but this doesn't actually make much sense because it's all just letters and it's jumbled up. So how can we, so instead of doing that, how can we actually interpret L, K, and R that we obtain? So we can interpret this by the values of L, K, and R are able to be obtained in the equation, with the equation that requires the input of values V, C, D, A, R, and W. So basically, if a company wants to find this, their labor, their capital, and revenue that comes from it, they need to be able to input all of these values here from their research and their data and stuff. From here, we can also see that revenue is inversely proportionate to the usage of labor and capital. This means that less labor and capital we spend, the more revenue we obtain. This also makes sense economically. So from here, we can sort of just see that R is inversely proportionate to L and K. So if L and K is big, then R will be quite small. But if this is quite small, then R will be bigger in comparison. And so that is my final interpretation for question number 3. Okay, so that is all for my presentation for my midterms. Thank you for watching.